So to continue our functional group chemistry series, we're going to have a look at the different types of reactions that our alkenes undergo. And so we'll start by defining what an alkene is by looking at its general formula. So the general formula of alkenes is CnH2n, where n equals any number. And we can see, if we remember back to our video on alkanes, that instead of having H2n plus 2, we only have H2n, which means we have less hydrogens in alkenes than we do in alkanes. And this is simply due to the presence of a double bond between carbons, which means there's less room for hydrogen. And we'll have a look at what that means. So let's make n equal 3, meaning we have 3 carbons. Now we're going to be drawing out an alkene here, so we need to have at least one double bond between our carbons. So let's pop one here. So because our carbons can form 4 bonds, if we have a look at our first carbon here, we can see that it has 2 bonds attached to it. And so it has the capacity for 2 more bonds. So let's draw in 2 more bonds. Let's have a look at our second carbon now. We can see that it has 1, 2, 3 bonds, so it can form 1 more. So let's fill that in. Finally, looking at our last carbon, we can see that it has 1 bond, so it can form 3 more. And so we can see here that because we have this double bond, rather than having 3 hydrogens attached to this carbon and 2 attached to this one, we have 2 attached to the first carbon and only 1 attached to the second because of this double bond. And so if we count out the amount of hydrogens we have 1, 2, 3, 4, 5, 6. So our n being 3 and our 2n being 6 satisfies our rules. So now we've understood what alkenes are, and we've had a look at the general formula and understood that it has less hydrogen, so it is less saturated than alkanes. So now let's have a look at the different types of reactions that alkenes undergo. A key understanding to take away is that our alkenes are more reactive than alkanes. And this is due to the presence of double carbon-carbon bonds. And so because we have double bonds present between our carbons, we can break one of the bonds in the double bond and add something on. So for example, if we look at a simple alkene here, if we break one of the bonds in the double bond here, then we have the capacity to add 1 more bond on here and 1 more bond on here. So we can add in some stuff. Due to the carbon double bonds, alkenes are more reactive than alkanes. And critically, alkenes are able to undergo addition reactions. So I have a video up on my channel already detailing the difference between addition and substitution reactions. So check that out if you haven't already. But like I said, the critical thing to understand is that alkenes will undergo addition reactions due to the presence of a double bond, as opposed to just substitution reactions, where an element has to be taken off the compound before another one can be added. So we have 5 addition reactions that we're going to learn about for alkenes. So the first addition reaction that we'll look at will be the addition of halogens. So we've already touched on in previous videos how our halogens are our group 17 compounds found in the second last column of the periodic table, and they exist diatomically, so they come in pairs. So we'll look at the addition of halogens to alkenes. The second addition reaction that we'll focus on will be the addition of hydrogens. And the addition of hydrogen is also sometimes referred to as hydrogenation. The third type of addition reaction will be looking at the addition of hydrogen halides. Now, hydrogen halides, as the name sort of alludes to, is where we have a halogen bonded to a hydrogen. So for example, we might have the bromine hydrogen halide, so where we have the halogen bromine bonded to the halogen hydrogen. Another example is the chlorine hydrogen halide, where we have the chlorine halogen bonded to a hydrogen. So it's simply where we have something from group 17 bonding to a hydrogen. That's what we call our hydrogen halide. So we'll look at the addition of hydrogen halides. We'll also look at the addition of water. The addition of water is referred to as hydration, not to be confused with hydrogenation. And the last type of addition reaction we will look at is a special type called polymerisation. So let's start by having a look at the addition of halogens. We've come across halogens before. Remember, alkanes also react with halogens, so both alkanes and alkenes will react with halogens. But they're going to do this via different mechanisms. So remember, the reaction of alkanes with halogens is a substitution reaction, whereas for alkenes, this is going to be via addition because of the presence of a double bond. And so if we think back to our alkanes, for this substitution to be initiated, we needed ultraviolet light, because we needed to split the diatomic halogen in order to swap it with one of the hydrogens already on the alkane. So UV light is needed to initiate the split of the halogen. Whereas with addition of halogens to alkenes, it's going to use both of the atoms in the diatomic halogen. And so as a result, it doesn't need UV light to split the halogen. And so we can use bromine water to distinguish between alkanes and alkenes. So let's unpack this. And so like we've already said, the reaction of alkanes with bromine, which is an example of a halogen, is going to require UV light to be initiated. Whereas if we're going to react alkenes with bromine, we're not going to need UV light. And so if we have in one test tube alkanes with bromine water, and in another test tube we have alkenes with bromine water, if we put these test tubes in the dark, our alkanes are not going to have a reaction with our bromine because we're in the dark, there's no UV light, and so that means that the reaction cannot be initiated. Whereas if we're in the dark and we have our alkene test tube, a reaction is going to take place because it doesn't need UV light to be initiated. And so what I've just written there is that in the absence of UV light, the reaction between bromine and alkanes cannot be initiated because there's no UV light present, whereas with the reaction of alkenes with bromine will proceed anyway because it doesn't need UV light to be initiated. And so the other thing to understand is that bromine water is orange in color, and so as bromine is used up in a reaction, the solution color should change from orange to clear as the bromine is used up, whereas if bromine is not used up, there will be no color change. And so we can use that information to distinguish between alkanes and alkenes. With our alkanes in the dark, we're not going to see a color change. Whereas with our alkenes, because a reaction is going to take place, that bromine is going to get used up, and so we are going to see a color change going from orange to clear, or from orange to colorless. So let's go ahead and tick that off. The next type of reaction that we were going to look at is the addition of hydrogens, also known as hydrogenation. So the addition of hydrogen is going to turn our alkenes into alkanes. And so I'll quickly draw out an alkene. But before I proceed explaining this point, I just wanted to point out that if I was going to draw this according to Vesper theory, we obviously wouldn't draw it like this. It would look a little bit more like this. Because if we understand our Vesper theory, we know that the angles are going to be different, where we have different electron domains. And so wherever we see a double bond in organic chemistry, we're going to see this bend in the molecule, as we see here. I've just been drawing out our alkenes this way, and I'll continue to do so for this video, just for ease of understanding. Going back to our main point, we've got an alkene here. Now we want to understand what the addition of hydrogen is going to do. So if we're going to add H2, so hydrogen, that's going to require us to break one of the bonds in the double bond. And so now, because that bond has been broken, we now have space to add more stuff on, because our carbon needs to form 4 bonds, and so far this carbon only has 3. This carbon only has 3, which means we have provision to add something on here and to add something on here. And that something is going to be obviously our hydrogens, because we're doing an addition of hydrogen reaction. So we add those hydrogens on. And now if we have a look, our product is an alkane. So we have just single bonds between our carbons and hydrogens coming off all our carbons. So this is an alkane. So we started with butene, and now we've ended up with butane. The last thing to understand in terms of hydrogenation reactions is that it does require a nickel catalyst. And also, this reaction best takes place in conditions where it's 150 degrees Celsius. So that's as much as we need to know for our addition of hydrogen reactions. Let's go ahead and tick that off. The next type of addition reaction that we need to look at is the addition of hydrogen halides. So we've already defined that a hydrogen halide is where we have a halogen, for example, bromine, bonded to a hydrogen. So that's a hydrogen halide. Now our addition of hydrogen halides is going to produce a halogen alkane. So let's have a look at what that means. So if we have this alkene here, which hopefully we can see is ethene. If we were to add a hydrogen halide, so let's say for example the bromine hydrogen halide, we're going to break one of these bonds in order to add our bromine and our hydrogen. And so we can see that the addition of our hydrogen halide to ethene has now produced bromoethane. Let's now have a look at the addition of water, which is also referred to as hydration. Now, hydration, we need to understand that it requires a sulfuric acid catalyst. So the formula for sulfuric acid is H2SO4. So let's have a look at how this sulfuric acid catalyst is going to help us in the addition of water. So let's say, for example, we have ethene once again. So I'll draw that out like this. So we have ethene here. Now we've talked about how we're going to have a sulfuric acid catalyst. So let me write that in. So what our sulfuric acid catalyst is going to do is it's going to have an intermediate step in which it splits into its ions, so the H plus ion and the HSO4 minus ion. And these ions are going to attach onto our alkene. And so remember, in order to facilitate the addition of anything, we need to remove this double bond here. So now that that's done, remember our main goal is to have the addition of water. So our water is now going to come along and split into its ions via hydrolysis. So it's going to split into a H plus ion and into an OH minus ion. And it's going to replace the ions that came from the sulfuric acid. So it's going to replace them. So we're going to have this H plus swapping for this H plus. And we're going to have the HSO4 ion from our sulfuric acid swapping from the hydroxide ion from our water. And so that's how we get the addition of water onto our alkene. So we needed that H2SO4 sulfuric acid as an intermediate step in order to prep our alkene to receive water. So just don't forget that the addition of water to an alkene requires sulfuric acid as a catalyst. Let's go ahead and tick off our hydration reaction. The last type of reaction that we need to look at for our alkenes will be our polymerization reaction. So in terms of polymerization, let's say we have two ethene molecules. We've got ethene, and we've got ethene here. Now we can add these two together. How do we do that, you might ask? Well, obviously being an addition reaction, we're going to break our double bonds. And in breaking our double bonds, this carbon here has room for one more bond. So we put that in. Same with this carbon here. It has 3 bonds right now, so we can take one more. And so as a result, we can put them together. What about our outer carbons? They only have 3 bonds on them. They still need one more bond. And so we simply indicate that by drawing in 2 lines at the end. And so we've added our 2 ethenes together. And so when you go to name this, you might be tempted to say 1, 2, 3, 4. Oh, this is butane. But we need to understand that because we started off with 2 ethene molecules, what this is going to be called is polyethene. And essentially you can react a bunch of ethenes together. You might react not just 2 ethenes together, you might add 3 ethenes together, or 4 ethenes together, or 5 ethenes, or 6. They will all still be called polyethene because it's simply a polymer made up of ethene monomers. We've seen an example where we've reacted 2 ethene molecules together. We could react 3 ethenes together, we could react 4 ethenes, so on and so forth. And also we could have reacted propenes together, we could have reacted butenes together. And so we name the polymer based on whatever monomer we started with. So because we started with ethene, we call ours polyethene. If we started with butene, we would call it polybutene, so on and so forth. And so that concludes our studies of the addition reactions that alkenes undergo. And so hopefully now you've understood that alkenes undergo addition reactions by breaking one of their double bonds, and that gives them the ability to have things added onto them. We've looked at 5 addition reactions for alkenes, involving the addition of halogens, the addition of hydrogens, the addition of hydrogen halides, the addition of water, and polymerization reactions.